Hi everyone, I'm Karidu and thank you for coming to my project presentation. And my project is focusing on engineering building 2, 28 GHz millimeter wave channel sounding measurement. And here are the keywords: millimeter wave, channel sounding, non-line of sight, indoor, and reflector. About this project, millimeter wave is very important in 5th generation communication because of its high available bandwidth and high achievable data rate. However, its propagation and coverage is seriously affected by the characteristic of millimeter wave, especially in non-line of sight scenarios. So in this work, we explore the use of a passive sphere reflector to improve millimeter wave signal coverage in an indoor non-line of sight scenario. First, I'll make some introduction on some basic concept. Since the millimeter wave, the channel sounding, and the non-line of sight is already introduced by Professor Ismail in class, so I will only introduce the National Instrument millimeter wave transceiver and PXI platform. National Instruments millimeter wave transceiver system is a modular set of hardware that can be used for a variety of applications from channel sounding. This system is built on the PXI platform and provides a flexible set of modules that can be combined in a number of different configurations to meet ever-changing research needs. This hardware combined with LabVIEW provides an excellent platform for millimeter wave communication prototyping and helps engineers innovate faster. And here is the system scenario used in this measurement. The system consists of two PXI classes with the transmitters in one classes and the receiver in the other. This configuration is well suited for making channel sounding measurements. With this configuration, one can physically separate the transmitter and receiver in different environments. Because of the modular nature of this PXI-based system, extra hardware can be easily added to accommodate different research needs. For example, adding more receive channels for more accurate angle of arrival measurements. And here is the hardware for this measurement. The left table is the receiver and the right table is the transmitter. And before the measurement setup, we have to set up the hardware first. And the first step is synchronize the transmitter and the receiver's clock. And the clock generates 10 MHz pulse per second signals. As we can see here, the rubidium clock here. The PPS output from one of these clocks, which is the transmitter, is connected to the input of another clock. So the clock of the transmitter and the receiver are synchronized. Once it is synchronized, the connection can be removed. And another important step is the calibration. The channel impulse response due to the hardware might seriously affect the measurement. So a calibration is conducted to compensate the non-flat frequency response from the measurement hardware. The transmitter and the receiver is connected through a calibration cable. The non-flat frequency response is measured and then calibrated. So once these works are done, we can start the measurement setup. The measurement was conducted in Engineering Building 2, basement corridor. And the left picture here is the transmitter, and the right picture here is the reflector. It's the receiver, and here, this is a sphere reflector. Let's take a closer look at the reflector. It is a sphere reflector mirror surface as shown. It is implemented to expand the mmWave coverage, and it is 30-inch in radius. So this scenario can be shown more clearly in this two-dimension plot. It is created in a non-line of sight situation. Here is the transmitter, and the receiver will be located in this grid. And we can see here that there are no directly line of sight paths here. So the receiver only only receive the signals, only receive the reflected signals. And the transceiver is fixed. The receiver will be manually moved at different positions in the X and Y plane of the corridor to form a 53 × 6 receiver blocks. For example, we start in this row here, and then in this row. The CIR power and the corresponding time at each block is needed. To conduct this measurement, start the testing platform first, then immediately run the MATLAB file to measure the time of each block. The platform measures the power every 20 milliseconds, and each block's power can be shown by comparing the time in the MATLAB file that generated and in the file generated by the platform. And of course, there will be a time delay in starting the platform and the MATLAB, which is about 0.5 seconds. This should be taken into account. And let's look at the measurement result. This figure shows the measurement data. The X label is the time of the measurement, and the Y label is the received CIR power. And the right line here is the 53 × 6, which is 318 for all the grids. After finding each grid's power, we can use the MATLAB to draw a power grid. Note that and here, the first 3 lines is wiped before generating this figure, because it is not exactly in non-line of sight case. And then we can make a comparison with the no reflector case and the sphere reflector with a rough surface. And we can see from here that the smooth one versus the no reflector case, it has about 20 dB max gain, and the average gain for the sphere reflector with a smooth surface is about 10 probably. And also the reflector with a smooth surface works better than the rough one. But the rough reflector, it has a more equal power distribution. Why the smooth works better than the rough one? Because a rough surface is more likely to provide multipath reflection that are not contributing to the received power. They will go to different directions, and only part of it will reach the receiver, which will result in a lower received power. Another reason, I think, is due to the structure of the rough reflector, where it's an aluminum sheet and wrapped on the original smooth surface of the mirror ball. So there might be some absorptions on the mmWave. Then let's look at the cumulative density function. The CDF plot of received power for 2 different sphere reflector and no reflector case are shown in this figure. For no reflector, which is the red line here, the yellow line here, we have the lowest received power. It can also be observed that the rough reflector, which is the green line, has much lower received power as compared to the smooth one, the black line here. And the average gain for the smooth surface reflector, we can see that it's the distance of these two lines, which is about 10 dB, maybe a little bit less than 10 dB. So we can make a conclusion here. First, of course, this sphere reflector worked. The coverage and the gain increased, and the path loss decreased. And also the sphere reflector with a smooth surface used in this measurement has a 20 dB max gain and an average 10 dB gain versus the no reflector case. And besides, the smooth surface works better than the rough surface. Thank you for watching, and I want to thank Wahab, Ozgur, and Professor Ismail for helping me on this measurement. Thank you.